Hey, today we're going to look at some of the basic theorems about series. Keep in mind that our main goal in our study of series is always going to be to determine whether or not a given series converges or diverges. We've already answered that in the special case where the series is geometric. Geometric series converges precisely when the absolute value of the ratio r is less than 1. But now we're going to be looking at all kinds of series, and so we need all kinds of different ways to determine do they converge or do they diverge. First of all, let's remind ourselves that for any sequence of terms a sub n, we define the series sum n equals 1 to infinity of a sub n, which you can think of intuitively as a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 and on and on and on forever. But precisely it's defined as the limit as n goes to infinity of the sequence of nth partial sums s sub n, where s sub n is just the sum of the first n terms of the sequence. Now, suppose we have a series, sum n equals 1 to infinity of a sub n, that converges to some value L. That's the same thing as saying that the limit as n goes to infinity of the sequence of nth partial sums s sub n is equal to L, which is to say that for very large values of n, the nth partial sum s sub n has to be very close to the value L. And since we're talking about very large values of n, well, then it doesn't really matter if we're talking about the nth partial sum or the n minus 1th partial sum. They're both very, very close to L. Which is to say that as n goes to infinity, the difference between any two consecutive nth partial sums has got to be approaching 0. But what is the nth partial sum? Well, it's the n minus 1th partial sum plus one more term, in particular the term a sub n. Or, applying a little algebra, the nth partial sum minus the n minus 1th partial sum is just the term a sub n. And putting all this together gives us this theorem that if the series sum n equals 1 to infinity of a sub n converges, then the limit as n goes to infinity of the terms a sub n must be equal to 0. And we usually look at this theorem in its what's called contrapositive form. It's equivalent to saying, if the limit as n goes to infinity of a sub n is not equal to 0, then the series sum n equals 1 to infinity of a sub n must diverge. And this is sometimes known as the divergence test. If you can show that the terms of a series are not going to 0, then the series has to diverge. And if you think about it a little bit, this is actually fairly intuitive. Suppose the limit as n went to infinity of some sequence a sub n was equal to, say, a tenth, for example. Well, that means if you go out far enough in the series, it starts looking like plus a tenth, plus a tenth, plus a tenth, plus a tenth, forever and ever and ever. And if you keep adding a tenth forever and ever and ever, you're going to get infinity. And so this is just an intuitive way of looking at this. Unless the terms are going to 0, there is no way for the series to converge. Let's do a quick example so that you see what I'm talking about. Let's look at the series, the sum n equals 1 to infinity of n squared over 3n squared minus 1. And let's look at the limit as n goes to infinity of the terms of this series. Well, there's more than one way to do it. Probably the easiest is to use L'Hopital's rule. And by L'Hopital's rule, since this limit is of the form infinity over infinity, it's equal to the limit as n approaches infinity of the derivative of the numerator divided by the derivative of the denominator, and 2n over 6n is just 1/3. And so these terms are going to 1/3 as n goes to infinity. And that tells us that the series sum n equals 1 to infinity of n squared over 3n squared minus 1 diverges because the terms aren't going to 0. If you like, you can say by the divergence test. But it diverges because the terms are not going to 0, so it can't possibly converge. If you recall, we looked recently at the geometric series, sum n equals 1 to infinity of 1/2 to the n minus 1, which you can think of intuitively and informally as 1 plus a half plus a quarter plus an eighth and on and on and on forever. And we had a formula for that, and we found that not only does it converge, but it converges to 2. And you'll notice that just like our theorem that we developed today guarantees, the limit as n goes to infinity of the terms of this series is equal to 0. I want to look now at a very famous example. This series is known as the harmonic series, the sum n equals 1 to infinity of 1 over n, which is informally 1 plus a half plus a third plus a fourth plus a fifth, and on and on and on forever like that. And there's certainly no doubt that the limit as n goes to infinity of the terms of the series, the limit as n goes to infinity of 1 over n, is equal to 0. But consider these terms, 1/3 plus 1/4. Well, 1/3 is bigger than a fourth, so 1/3 plus 1/4 greater than 1/4 plus 1/4, which is equal to a half. And then if you group the next 4 terms, well, 1/5, 1/6, and 1/7 are all larger than 1/8. So 1/5 plus 1/6 plus 1/7 plus 1/8 is greater than 1/8 plus 1/8 plus 1/8 plus 1/8, which is also equal to a half. And you can keep doing that. Group the next 8 terms, and you'll find that those add up to something greater than a half. And group the next 16 terms, and you'll find that that's greater than a half, etc. And seeing as you can keep doing that forever because there are infinitely many terms to work with, we get that the series, the sum n equals 1 to infinity of 1 over n, is greater than 1 plus a half plus a half plus a half plus a half, and on and on and on like that forever. And if you add a half plus a half plus a half forever, well, that grows without bound. And so this series diverges to infinity. And so this is a very important example. Here we have that the terms, the limit of the terms of the sequence is equal to 0, and yet the series does not converge. In particular, our theorem said that if the series converges, then the terms of the series go to 0. The limit as n goes to infinity of the terms of the series goes to 0, is equal to 0, which you can also turn around and interpret as meaning if the limit of the terms is not equal to 0, then the series diverges. But what you can't do is say, if the limit of the terms is equal to 0, then something happens. Who knows? If the limit of the terms is equal to 0, the series might converge and it might diverge. Here we see an example of a series where the terms are going to 0, but the series diverges. A moment ago, with the geometric series 1/2 to the n minus 1, we saw an example where the terms were going to 0 and the series converged. And so the only way you can use the divergence test is to say that a series diverges when the terms do not go to 0. If the terms do go to 0, you can't use the divergence test. The series might converge or it might diverge. And that's important enough to write down and say again, if the limit as n goes to infinity of a sub n is equal to 0, then the series sum n equals 1 to infinity of a sub n might converge or might diverge. You don't know. Okay, here's another theorem for you. It comes straight from the limit laws for sequences. If we have 2 series, I've left off the n equals 1 to infinity, so just imagine that they're there. This is just shorthand. 2 series, sum an and sum bn, and they both converge, and c is some real number, then from the limit laws, you get that the series of a sub n plus b sub n converges to the sum a sub n plus the sum b sub n. And similarly, you get that the series of the product of the terms converges to the product of the series. And finally, and not surprisingly, if you have the sum of some constant times some series, you can pull the constant outside of the series just like you could with limits and derivatives and integrals. And finally, one more theorem that will occasionally be useful for us. If you remove finitely many terms of a series, that doesn't change whether or not it converges. In other words, if you're looking at the series sum n equals 1 to infinity of a sub n, and sum n equals 65 billion to infinity of a sub n, well, either they both converge or they both diverge. How come? Because the sum of the first 65 billion terms is just some number. And so, they converge to different values, but it's not going to change whether or not you get infinity for both of them. You either get a number for both of them or infinity for both of them. For example, we've already seen that the geometric series, the sum n equals 1 to infinity of 1/2 to the n minus 1 is equal to 2. And if instead we considered the series sum n equals 5 to infinity of 1/2 to the n minus 1, well, it's the same series except missing the first 4 terms. So you'd get 2 minus the sum of the first 4 terms, some finite number. Still converges, just converges to a different number. Okay, those were some of the very basic theorems on series. You are not quite ready for the next homework assignment. One more video to go, and then you will be. See you soon.